Uh,
Hi.
Hello, I don't see any. I don't see where is resume recording. Okay, so there is a theorem of Wooden which I didn't know. I only learned this week, and it's very nice, and it's in this neighborhood. It's easy to prove, and I think it's very useful. So why don't I prove that today? It's kind of similar to the things that we need to prove anyway, but it's a little bit easier. So suppose we can assume ADR, but I don't. Let's assume ADR just for simplicity. Plus V equals L of R cell of BST.
Excuse me, I'm not sure if it appeared earlier at the seminar, but what is AD plus?
Yeah, well, we don't need it.
General.
Yeah, it will take me a long time to say. We don't need AD plus. I guess we might need. No, I don't think we need. No. So, I mean, it's an AD with. It's not really a little bit more. It's a lot more, but it takes forever to explain what it is. So why don't we? Usually, people say just ignore the plus and think of it as just AD, right? But not easy to explain. Okay, so we do ADR plus V equals L of P of R. Now suppose lambda is an ordinal. We don't even need a cardinal, I believe. Ordinal less than theta, and U is an outer filter. Lambda. And then U from odd into MU is D, which is, basically odd lambda U is the outer core embedding. Then JU lifts to a generic embedding. G sorry. Such that, of course, I mean, lifts usually means that Christopher is here. Usually means that strictly to V is JU. I guess I want to say hard. Okay, so it's saying any ultra power on ordinals. You take basically the ultra power can be realized as a restriction of a generic embedding. Right.
What is mg?
Something.
Okay.
It's the generic ultra power. So G is gonna be generic ultra power by something. By some, yeah, it's gonna be generic ultra power.
So you're saying there exists some g?
Yes.
Okay.
Right. So here is the proof. All right, so we fix. So what is the idea? Basically, we have an ideal R. Okay, so we're going to transfer U onto R. And then show that the ideal is precipitous, the ideal that we get on R. Okay, so let I be map onto lambda, right? Surjection. This exists because lambda was less than theta. Remember, lambda is below theta. Okay, so so we have, we have lambda here, right? So let's say this is alpha, and this is my lambda, and then we have the reals. So there are many things that get mapped to this, yeah. There are many reals, that get mapped to this, and many reals here that get mapped to beta, etc. So we want to ask, given an alpha, right? So given a subset of reals, we want to ask how many alphas have pre-image in that real, in that set. So look at these sections that get mapped to ordinals and see if your set intersects many of them. If it does not intersect many of them, then call it small, right? So there's IU, our set of reals, the following ideal. Then X is in IU, if only if X for U almost all alpha X does not have a code of alpha. So what does this English sentence mean? This means that the set of alpha less than lambda such that alpha has a code in X. What that means is that X intersects the section. So that means pi inverse alpha intersection X is does not have, right? So it's empty. Belongs to, that's what it means. Okay, so this is the ideal. And okay, so let's just record a remark. X is IU positive. If you may ask, why is this an ideal and not an ultra filter, right? Because it could be that both X and X complement, right? Meet for measure one many alpha, they both have codes for alpha. So this means that the set of alpha less than lambda pi inverse alpha intersection X is not empty. Belongs to U, right? So for measure one many places, you do have a code, then you're positive. Now you're not necessarily in the filter, but you're positive. So X and X complement both can have this property, right? It's not a bijection, it's a surjection. Okay, so that's why we get an ideal. Okay, I don't want to verify that I is nice. Let's just prove. What is the idea for proving the first? So, you know, we want to see basically that J U G is generic for basic. So what we will do is no matter what generic you pick. So let me write it more clearly, right? Because that's not what we will. What's written here is that no matter what generic you pick. So I want to see if G is EIU generic, and GU is a desired. Sorry. And IG equals what is, do you know what what this is? So this is the offset of IU positive sets. Measured by inclusion, right? So A is less than B if and only if A is included in B. So stronger conditions shrink it, right? And then of course, when you force with it, the generic object is always an ultrafilter. So the generic is an ultrafilter. Over, if you force with any ideal, the generic will be ultrafilter over the base thingy. The base now is reals over the reals, right? Okay, so this is the ultra power embedding. So pi g is the ultra power embedding. Which means what? So what is the ultra power? Ultra power V by G. This is just the equivalence classes of G, where F is a function from reals into V, F in V, right? And then membership is, you know, two functions are equivalent if they agree on a measure one set, right? And of course, Fg belongs to Hg if only if the set of reals such that f of x belongs to h of x is G, and IGA is the constant AG where EIX is equal to A. Okay, so this is the setup. All right. So it's clear what we're proving. We have an ultrafilter on some ordinal and a real subject onto it. And what we do next is we look at the codes for ordinals in real codes for ordinals less than this ordinal. This is lambda. Then I say x is small, right? Set of reals is small if it does not have codes for most ordinals, right? And then that's the ideal that we get. Okay, so the first lemma.
Sorry, is watch theorem true?
Can you say again?
Is watch theorem true?
Well, we're about to prove it, right? So we don't know yet, but there are two things that we have to prove. We will prove Cauchy's theorem, and we have to prove that the ultrapower is well founded. Like there's no guarantee when you have an ideal and you're forced with it. There's no reason to believe that the ultrapower you get, this pi g, this alpha vg is well founded. So we need to prove it's well founded. To prove it's well founded, we need to show exactly what we want to prove, namely this. Right? If we show this, it would mean it's well founded because it would mean that a little bit stronger fact than this. Okay, let's
If we simply extend the original map, that's not enough, right? Because we don't have DC or something. Is that a problem? Because if we know that we are well founded on the ordinals.
Yes, then you're well founded, right?
Yeah, but is this a use of DC? Like well founded, ill founded doesn't necessarily mean there's
ordinals, so I'm not really sure if would you need DC.
I mean, to find decreasing sequence, you need DC, no? So to say well-founded means the same as there's no decreasing sequence. And my question is whether...
Yeah, I understand the question. I'm not sure if we need DC though.
I mean, if you're below theta, then DCR is enough, right?
Can we... my feeling is that you will avoid DC in the standard ways. One usually avoids DC in this context, but let's just go on and see if it shows up, right?
Oh, maybe I'm confused because we're using HOD anyway, right? So we have a natural choice function.
Yeah, but you want to argue that the ultrapower V is well founded.
Then V is model of L of P of R, right?
Let's just go on because I think it's better to go on and see if it comes up.
Yes.
Okay, so let's do lemma. So what we want to what this lemma says is that the functions on IU functions are decided by the ordinal functions. So suppose X is a subset of reals, is IU positive, and you have F, which maps X to the ordinals. Then there exists an F star from lambda to the ordinals, such that the set of T where the functions agree, right? Such that F of T remember pi was mapping reals. Pi was mapping reals onto lambda, right? Such that f of t is the same as f star pi t is I u positive. So what does this say? This says we need this stronger version to prove our fun. No, so you see, we don't need DC anymore, right? Because this would tell you that. So what does this say? Remark. This means that that there exists a map K from the ordinals of out V G, meaning whatever out VG things are ordinals, into the ordinals of out V U. Oh, and so maybe we need DC there. I don't know.
Yeah, I think in the end you still need DC to get that the ill-foundedness goes down along embedding, right?
So we have and this is well founded. Yeah, so we probably need DC.
But maybe like DCR and the fact that we are in L of P of R is enough, right? To get the ill-foundedness into the range of.
I don't think you need, no, you don't, because you can always bring it down to a place where you have a DC. So I don't think you need. You know, it's omega many functions, and these functions, the codes of these functions, yeah, they could appear. Yeah, I don't think you need, but I don't see the proof at the moment. Let me erase it and then we will discuss next time. There are these usual tricks where you say, okay, look, all I needed is some initial segment of the universe, and then DC holds there. So what is this map? This map is going to do K of the representative of F. You're going to send this to the F star of U, right? But F star is as in the claim. That's what the lemma shows. Okay. All right, so let's prove the lemma. There is also K such that this is K and K is order preserving. That's this, this is key, right? Okay, so proof of, and it's order preserving because, you know, it's the same function, right? It's the same ordinal function. Okay, so proof of the lemma. It's not hard, right? Because so let A be the set of alpha such that X has a code for alpha. Where A is the set of places where X has a code. And I know, so for each alpha, if each code from X, F gives me some value, but I can pick the least one, right? So let F star of alpha be, let's say 0 if alpha is not in A, and minimum of f of x, f of A, minimum f of A a. Okay, let's just pick up a little. So for alpha in A, let B alpha be the set of beta such that there exists an A in I inverse alpha intersection X such that f of A is beta. Right? So look at all the possible values that the codes of alpha, which are in X, give you, and then pick the minimum one. So now let f star alpha be 0 if alpha is not in A, and the alpha is in A. Right? And now we have, you see, if, so what is the important remark? If alpha is in A, then there is an A in X intersection pi inverse alpha such that f star alpha is f of alpha. Right? So this means that the set of A such that f of A, set of A in X, that f of A is equal to f of star of pi of A. This should be A, yeah, right? So the set of A for which f of A is f of star of pi of A belongs to IU. Sorry, it does not belong to IU, pi positive. Right? Because why? Because this set contains A. Because let's call this Y. Because the set of alpha such that there exists an A in the set of alpha such that pi inverse alpha intersection Y is not empty. Contains A. And A was measure 1, right? Because for each alpha, there is some member of X which attains the same value. F star alpha is the same as f of A. So we still keep A fixed. Okay, so this is the proof. What is it that we wanted to prove? We wanted to prove that on an I positive set, this ordinal function is the same as the real function. So you have it. So that's the proof. That one is easy. The other one is harder, not hard. And that's this proof. The proof that I'm about to do is the proof of Walsh's theorem, and this is the proof of Walsh's theorem that we use in all of these situations. Why don't I just write data regular there, because to avoid all sorts of questions that people might be asking. Plus, so let's say eta plus data is regular, right?
But my DC concern is nonsense. I think that ill-foundedness goes down works without DC. I was just confused.
Mm-hmm.
You can just you can just pick the rank minimal element of a set, right? And
yes, yeah. No, the isomorphism will be okay, but but it could come up in the other. Let's just say data range.
Yeah, in the washer's theorem, maybe. Okay.
Okay, so the proof of Washer's theorem that I'm about to do is the same. This proof shows up in many such arguments. That you want to take a algebra of a model of determinacy, you want to prove Washer's theorem holds. This is the argument, basically. So what is it that we want to prove? Maybe, okay, let me write down the lemma and explain why this is what you want to prove. Suppose X is a subset of reals, is IU positive, and F X into V minus MT is a function. Right? Cauchy's theorem basically tells you that you have a choice function for F, basically on a I positive set. Not you're allowed to shrink the domain, but you have to have a choice function. So then there exists an IU positive set Y, which is a subset of X, and the function V such that G is going to pick a member of F, right? Such that for every T in Y, G of T is picking a member of F of T. So what is it saying? You give me a function that kind of a family of sets indexed by reals. I can find the I positive set on which I have I can choose points from the sequence you have. This is why is this Cauchy's theorem? Well, Cauchy's theorem is saying what? So mark Cauchy's theorem. You want to prove something like if the want to see something like if the set of T for which V thinks there exists an X there exists a U such that V U and then some sequence of functions, right, applied to this point T. This is not in IU, then I can find then there is G. Sorry, then so let's call this X. Then there is Y, which is a subset of X. Y is not in IU, so it's positive, and G from Y into, maybe I call this function F because H will be another function. So there's a sequence of functions, right? There will be finite sequence of functions to which you will apply T. And so you can find an I positive set and a function defined on it such that the set X prime, which equals to P in X, well, I guess it's just Y. Such that for every T in Y, right, V things P holds of G T and H T. Right. So what's written here is that if for I positive many places you have a witness, then I can shrink my set and pick the witness for each point inside my smaller set.
Gregor, do you maybe want that the difference of x and y is small? Because it could happen that the generic hits x and misses y, right? That would be bad.
Oh,
So maybe the difference of x and y should be in
well,
there.
this is saying that the set of y for which it stands, right?
But did you say it stands? Did you say you can always find such y?
Yeah, for any x which with this property I can find.
Yeah, you're kind of putting denseness in there. Sorry.
Mhm. Yeah. Oh, so okay. Okay, so how is this? How does this relate to the lemma we have? In the lemma, it says I can pick, make choices. Here we're saying there is a function. Well, but now think of, so for each t to apply the lemma, right? That's for t in x, ft be the set of witnesses of for ht, basically. Okay, and then apply the lemma to that. So f of t is the set of all witnesses. Lemma is telling you can pick one, and that's it. That's what you do. All right, so it's this lemma that we want to prove. Proof of
Excuse me, just to ensure I'm less experienced with this stuff. So we're making basically like some inductive step of the Wash theorem here.
yes,
And
in
I
the
mean,
Wash
like
theorem, you would prove by induction. So if you imagine you
inductive
already
by quantifier, I mean.
I'm sorry.
So are we making here like inductive step for like adding one quantifier, one
Yeah,
existential
because that's the one.
quantifier?
That's the other quantifiers. The other operations are easier. That just follow
Okay.
from finite intersection. Things like the
Okay.
complex. The other ones are easy.
Okay, thank you.
This is exactly that. It's an inductive proof of Wash's theorem, and this is the hard case. Okay. So what do? We use. So we're going to use this assumption. This assumption is key in these proofs, because what does this assumption allow us to do? The V equals L of P of R. That assumption is allow us to pick, to transfer the set of witnesses, right? Each witness that we have is definable from some set of reals. So it's allowing us to we have a control of how the set of witnesses is defined. So let's go how we're going to use it. Okay, so for each t, that's going to be the first step. For each t, I'm going to look at an ordinal such that some set of reals whose weight rank is that ordinal is allowing me to define a member of f of t, right? So for t in x, x was the set on which f is defined, right? So for t in x, let eta t be the list such that for some set of reals b of weight rank let's say eta t or less than eta t, this doesn't matter. There is a member of f of t, which is OD from T. So the key fact that we use here, which has nothing to do with determinacy, is that assume v equals L of x, right? Then L of, let's call it something else. V equals L of z, and then every set is ordinal definable from a member of z and z.
It should be member of transitive closure of Z, right?
Yeah, let's say z is transitively closed. It's transitively closed. But the reals, I mean, for reals, that's so. If you apply that this theorem for power set of reals, you'll see it comes down to just set of reals because everything else is just generated by. Okay. Now you have to remember that the set of reals under determinacy are ordered by the wage rank. So there is a set of reals for which is definable. Okay, so there is the least wage rank for which you can pick such a thing. Okay, so the next step in all of these arguments is that the supremum of these etas cannot be equal to theta. So the next key fact, the supremum in x of eta t is less than theta. So here we are going to use the fact that theta is regular, right? What we could have done with the other ATR models. The cop omega case, that would have been okay. So
Can you do like sigma 1 reflection argument for
this? No, for this you do.
no, for the non-theta regular case?
Well, then I think you have to cut the universe.
I mean, why do you have to cut the universe? I thought like the whole point is
No, for the theorem, I think. Yeah, I'm not really sure if you can prove the theorem in the non.
take some. I thought you take some failure of this choice fact, and then you reflect it down by sigma 1 reflection, and then you use that something I don't know.
By reflecting, you will end up in the same place. I don't know if you can. I know this works for theta regular, cos theta equals omega, and yeah, cos theta is equal to omega and cos theta is regular. I don't know if it works in other cofinalities. So
What can you do in the cofinality omega case?
just a pigeonhole type of argument, I think.
And what this only works with this doesn't work with cofinality smaller theta pigeonhole?
Can I write down?
Sorry, yeah. Finish.
Let's finish arguments and then have a discussion, because then it's unclear what this discussion is about. Let's finish this argument. So next key fact is that the sup is theta. Sup is less than theta. It will also help me to remember the argument, right? Because it's not like everything is. If I do the proof, I will also remember the argument. And I'll be able to answer the question better. So if the sup is theta, right? Suppose sup eta t in x is theta. What this means is that I have, because theta is regular, this gives me a primal ordering, right? So now we have, let's see, so what do we have? We have less than or equal to, given by t is less than or equal to t prime, if only if eta t is less than or equal to eta t prime, right? And now this is where we use the irregularity. So this is where the other proofs could fail, right? So because theta is regular, length, the order of less than or equal to is theta. What this means, you can ask why. Well, suppose less than or equal to the length of that was some beta. Is some beta less than beta. Then define g from beta to theta by what? By g gamma is equal to eta t, where t is such that gamma is equal to less than the rank of t in the less than or equal to relation. Right? So if it was smaller, then you look at ordinal less than beta, something has that rank. You pick that thing that has that rank, and now you look at the image on this eta function. Okay, but the eta function is independent, right? If two things have the same order in the eta, if the two reals have the same rank in the less than or equal to star relation, then they have the same etas. So this is independent of eta. G is independent. G gamma is independent of the choice of eta. Sorry, choice of all of choice of t, and that contradicts. So this is, if something fails about the confinality, then this is what fails, right? Because now we can have such a function if theta is not regular. Okay, so because theta is regular, this is the length. I should say that the cardinality is theta, right? So the length of the trivial ordering is theta. But that's contradiction, because that's a map of reals onto theta, right? But we cannot have such a oh, right? Because theta is the sup of all theta less than beta, which are surjective image of okay. The length of this parallel ordering is a surjective image of reals. Namely, if each real onto its rank, that's a surjection. Theta cannot be equal to something like that. So this is the contradiction. Contradiction to what? Contradiction to the fact that the sup is theta, right? Okay, so we have the sup t in x, theta t is less than theta. Okay, so now what does this mean? This means I can pick an ordinal between the sup and theta, and now look and pick a set of reals of that weight rank. So let now A be some. I think we should reserve A for set of ordinals. So let D be set of reals such that the weight rank of D is greater than or equal to the supremum of eta T D in X. Okay. So what this means is that I can now, well, we're not quite done yet. So what is the next idea is, remember what eta T is. Let's go back to see where eta T is. Eta T says, I am the least ordinal such that for some set of reals B of weight rank below myself, you'll define a member of f of t, right? Now we have a set of reals which is above all of these guys. So that means from the set I fixed down below, this set D, yes, I should be able to define modulo some other real. I should be able to define a B. A B from which you can define an f of t. Okay. So I guess we're going to use this argument one more time. So we will use, let me write here, remark. We will use D to define for each T set whose weight rank set B whose weight rank is less than eta T, and it defines, let me put it quotation mark, defines a member of F. So defines here means there is a member of it which is ordinal definable. But there is a problem. Each time D is above, remember the weight rank of D is above the sup of all of these etas. So this is okay, but each time you want to do that, a new real shows up, right? And so we need to say, so I need to pick a real. Is that clear? Right, so you have your set D somewhere here, and then you have the smaller etas, and I want to use this D to find continuous preimages down below, which work, but then every time you do that, a new real shows up. So which real should I use?
This is not only, is it not just uniformization now in the end? You just, you minimize the ordinary, like, you know that you always have this ordinary definable thing now. You minimize the ordinary, so the ordinary doesn't play a role, then you get a relation now from, get a relation on R times R or something, and you use uniformization.
Just ADR, shouldn't just ADR choose a real?
You have to set it up correctly, right? Because you want to say, look at those reals for from which I can define a B. And
Exactly.
then, can you say again?
I mean, yeah, you just have for each, yeah, you have a set of reals which give correct witnesses, right? For
That's right. However, let's see, I'm missing something. So if you look at, basically you have to look at all the sigmas from which you have the B relative to D, yes. But I mean, it's not independent of, so by G of T, my witness is going to be, you see that there are many reals that will give me a B. So which B should I pick?
I mean, that's just uniformization, all right? For each T, you get a bunch of reals. For each T, you get a bunch of reals.
Sorry, there is the T, yes, that is the T that's important. Sorry, yeah. So we look at the T is important. I need to pick a B relative to T. So yeah. So from each it's the T that's important, right? So I need to pick the B relative for each T. Okay, so now consider now the set of E, which is T and let's say B. Now B is gonna in R2, right? And now I want to say B is telling me relative to D, B is giving me a set which is defines a member of f of t, right? So so TB are in there if B codes a continuous function from omega into omega, and if B equals B inverse D, then there is a member of f of t order definable from B. This is my set. And now you pick the B. So by uniformization, right? Because AD implies uniformization, pick F from reals to reals such that for every T in X, this is T in X, right? For every T in X, T F of T belongs to E, right? And now I know that from f of t I have my definition. So now we can define G. So let GT be the least, the OD f of t least, right? OD least means you're minimizing the ordinals used to define the set. So OD f of t least member of f of t, right? And this is defined for every t in X. Unless we shrunk t at some point. Okay, let's just go back as it. So we want to prove this theorem, right? So we want to say I have a positive IU positive set and I have a function. Then I can shrink it such that for every t in y, gt is in f of t. So we have to shrink it somewhere. Or maybe we don't. Okay, so for t in x, let a dot t be the least such that for anyone wanted to say something?
And in the theta regular case, you don't need to do any shrinking here at all. It's just that theta regular proves a choice for R sequenced, choice for R indexed sequences.
Mhm.
That's what you essentially proved.
Now, this is what we proved. So that eta t be the least such that for some set of reals B of weight rank less than eta t, there is a member of f of t which is OD from B, right? And then every set in OD from a member of yeah. So that's then we argued that the sup of etas has to be less than theta. That's fine, right? Because that's where you use theta is regular. So we still our base set is x, and then so we found this d. Then we looked at the points. Yeah. So the domain is still x, and then we use uniformization. You don't have to shrink. I should. Yeah. You don't have to shrink. Yes, and for every t in x there is a b that we know. And that's it. This is the proof. So we didn't need to shrink. I think in Hugh's case, he is doing the argument that he sent me. He was doing it in L of AOR, and then there is you cannot use uniformization there. You have to use reflection, and I think there you have to shrink it. So let me make that a remark. This argument. Doesn't work. Models. Because they are regular fails with sorry, ADR fails. And so here we use sigma to 1 reflection. Here we use sigma to 1 reflection. And I think you need to use coding lemma. The reason you want to use coding lemma is because if there was such a uniformizing function, right, G exists, the coding lemma would tell you that it has to be somehow simple. And so now that's the statement you reflect. So the shrinking is going to come in when you apply the coding lemma, I think. Oh. Okay, so that's that. I think this proves the thing. Now, why doesn't this work in the COF bigger than omega case? Why does it work in the COF omega case? In the COF omega case, you could have this eta i's, right? So you already have an omega many sets. I think then you argue somehow that it's the completeness of ultrafilter, right? Because or something like that. I don't remember.
So you don't really prove the same lemma, but still a sufficient lemma, right? Because if you want to use the completeness of ultrafilter, maybe then you can still recover the same lemma in the end. But
which lemma are you talking about? This lemma, the uniform this lemma. So the etas can sup up to theta. This is the problem now. But if they sup up to theta, I think maybe this has to do with the fact that the ultra power will be cofinal at theta. So all I need to do is just look at the Solovay sequence and just prove for the universe up to theta. So prove this kind of lemma for each of these models, and then the ultra power could just be put together at the length at the omega step, because the map is cofinal at theta. So it could be because of that.
Okay, so
I can think about it for the next time. I think it has to do with shrinking. You have to shrink the universe. You have to somehow say, okay, I have the theorem for the model up to theta alpha, where theta alpha is strictly less than theta, right? Because then we proved for in the regular case. And then you put them together using the fact that the ultra power has to be cofinal at theta. I would think something like that is working.
So the problem is in the end that the cofinality needs to be smaller than the completeness of the ultra filter, so it doesn't work for any cofinality less than theta.
Or it could be that the cofinality should not be equal to the completeness. Because if it's bigger than the completeness, you can still prove that it's cofinal, the embedding. So I can figure out next time. Let's move on to the, because I don't remember. So this is the generic Washes theorem argument, and in our case, we are shooting for the tensor in on omega 1.
Sorry, Hero, but are we going to do this? So you're skipping now the discussion of the non-regular case altogether, or you'll do this?
Yes, no. We move
Okay,
on.
okay.
It's just the side. I mean, I wanted to say some that. I mean, Hugh, he knows this theorem for a long time, I think, but he never told it. It's, in my opinion, this is something extremely important. But so I wanted to tell you guys, because I think most people should know about this. It's such a basic fact. But no. There are a lot. I wonder how many things like that there are that only Woodin knows, and he's just waiting for some application to show up. I mean, that's how I've learned about this. It was some application that we were trying to do, and he's like, "Yeah, I know this thing." It's like, how come others don't know? Anyway, if you think about it, it's an incredible theorem. It's telling you why is this an incredible theorem? Because we know that theta is Woodin in hard, right? And now we know, so that's one thing. We know that theta is Woodin in hard, and we know, so therefore, and we know that the measures that witness the Woodiness of theta in hard are actually measures that come from V. So if you look at the proof of how you do that theta is not in the ADR case, but in the other cases, which I didn't do. Theta is Woodin in hard, and the measures come from V. So there's some ultra power U, ultra filter like U, which coheres hard. But what does that say? That says that the hard of MG, right? This guy, it says that there is some Woodinness, not for just hard, but for V, right? So this theorem is telling you that theta in the case which I didn't do, the one in the LOVR situations, in the non-ADR situations, is not only Woodin in hard, but is also Woodin in some sense Woodin in V, because you have these embeddings which cohere, which sort of cohere V. So it's a very nice result. Anyway.
Excuse me, maybe one more little question to sum up. Like, can you say briefly where have you used the assumption that V is equal to L of P of R?
Yeah, here we used it. There is this fact, which is saying that if V is OD, then every set is OD from the transitive closure of Z and Z itself. Now, in our case, Z is power set of reals, which is ordinal definable. So Z itself does not show up. Therefore, the only things that do show up are things in the transitive closure of Z. But then if you think about it, those will just be sets of reals. So when I wrote just above here, when I said let A dot T be the least such that for some set of reals of weight rank less than A dot T, there is a member of F of T, which is OD from B. We need to know that fact in order for this to make sense, right? Otherwise, why should there be such a, why does eta T make any sense?
Okay.
Yeah, so we need, that's why we need vectors. And there are lots of other, like for example, Naidian models that they're not of this form. So you can then say, can you prove this kind of theorems for Naidian models? I think that's very interesting. Or, you know, like Diane is working with all sets are UP, for example. Is this true for all set? You know, we are using this as an essential part of the proof that V equals L of Z. It tells you that witnesses to your statements can be reduced to witnesses to state. The witnesses can come from sets of reals. The witnesses are sets of reals. So you don't have that in other models. Okay, so let's go on because now I want to do at least a little bit of the stuff that we care about. So back to Them's ideals. So for this, we need to develop a theory of omega r natural powers of models of ABR plus V equals L of PR. And by the way, the same comment comes here. The V equals L of PR will be used in the Washes theorem. And so, as far as I know, it's open whether this proof, I mean, maybe it's not, but on the face of it, this proof is not known to work if you do it over an Naidian model. Because their parameters are not just, if you do the all sets are UB, the minimal one, their parameters can still be reduced to sets of reals. But if you do it over Naidian models, then there are countable sequences above theta. So you cannot just drop to sets of reals. Anyway.
What's call omega r ultra power?
I'm about to define these things.
Okay.
So you will see what it is. Notation. So I'm following Obrat's notes. So we will define an outer filter and then take an outer body. So notation. Mu is the Solvay outer filter on the omega 101 generated by clubs. That's what we proved, right? Every set contains a club. Every subset of the omega 1 R is either disjoint from a club or it contains a club. Okay, so here's the key. Oops. Why is this not writing? Something happened. Okay, suppose these are to the omega. So this is these are omega's functions, right? These are functions from. It's important to recall this because remember P omega 1 R. It's unordered countable subsets of reals. These are actual functions. So we want to say A is weakly. When is A omega? Okay, so A is weakly co-meager. What? Yeah. Okay. Let me write, and then I'll tell you what this is.
Sorry,
like.
like, is it a subset of R of omega? Because as it's written,
Hmm?
should it be subset rather than equality or what?
A subset. Yeah.
Okay, okay.
Very good. A is weakly co-meager below a condition. If for almost all sigma, if if there is a club, if for a club, if I would like to kind of think of, it does not matter that this is the it just so happened that on the ADR it's always measure ultrafilter is the club ultrafilter, but this would work for any normal fine ultrafilter. It's not important that it's the club filter. So let me not keep saying clubs. For some C in mu, for all sigma in C, image of P is in sigma. P is in sigma. And I will tell you what that means. And A intersection sigma to the omega intersection NP. NP is the open set given by P, is co-meager in NP. NP intersection right, so there are some topological terms. Let's see if people are familiar with these things, right? So, well, P is in sigma. P cannot be in sigma. Sigma is sets of reals. P is a function. So by this I mean the image of P is subset of sigma. Sigma to the omega is the Baire space, right? Give it to the topology that we usually give, and P is the open. And P is the set of all Q in sigma to the omega such that P is an initial segment of Q. This is what it means. Okay. So what is it saying? A is weakly co-meager below P if for club of sigma, so for almost all sigma, doesn't matter that it's the club filter or blah blah blah. For almost all sigma, the members of A are generic, are kind of self-generic, yeah. Let's see. So G is if F is in A, right? And F is a function from omega on two reals, right? So let sigma F be the range of F. Yes. So what this is saying is that F is generic enumeration of sigma F. What this condition is saying, basically. So it's saying that A is has a lot of self-generic points, kind of. Yeah, it's enumerating the thing. Members of A enumerate their ranges generically, basically. Okay. So A is weakly co-meager below P if for some large set of countable sets, A, it contains generic enumerations, many generic enumerations for that particular countable set. But for measure one, many of such sigma, right? Okay, so that's below P, and A is weakly omega. If it is weakly omega, below and right, so here is our ultrafilter. So define UG over power set of R to the omega V. A is in UG, if and only if there is a condition such that V thinks A is weakly omega co-omega below P. You may ask, why is this going to be an ultrafilter? What is the intuition that this will be an ultrafilter? Well, we have two ultrafilter-like theorems, right? So one is that we actually have the club filter is an ultrafilter, but it would work even if you were just working with some other ultrafilter, not the club filter. And also, because we are under AD, Bayer category theorem is true, right? So we know that every set has the Bayer property. Sorry, not Bayer category, Bayer property. Every set has the Bayer property. So that allows us to flip. That allows us to flip here, right? So if A is not, if A is not in UG, that means this set is not comega, right? That means its complement is comega on some set, right? That's the thing that the Bayer property is gonna. That's the intuition why this is gonna be an ultrafilter. And why do we say there is a P in G? Well, okay, so if A is not in UG, then for every P in G, that's false. But then you prove for each A, the dense many conditions that make, so for which A is either weakly omega below P or A complement is weakly omega below P, right? So that's basically Bayer property. In fact, I could just use BP, not AD, or just BP, I think. So suppose A is a subset of R to the omega, and E is in co omega R. So one of the following codes. Following holds. A is a weakly omega below P, or there is a Q such that the complement is weakly omega below Q. So let's do this proof and then finish, but I want to do this proof because you'll see why fineness is necessary. Okay, so we do this proof and finish. Proof. And then this proof, of course, gives you that UG is an ultrafilter, right? Why does it give UG as an outer filter? Because this, let me just write that remark and then. Lemma implies that the set of that for each A, the set of P such that A is a weakly omega below P, or a complement is a weakly omega below P is dense in all omega R. Right? Fix your A. The lemma, okay, so fix your P. We want to see that this and this dense. Fix your P. If A is not weakly omega below P, then I can extend it to a Q such that A complement will be weakly omega below Q. So that means this set is dense. Which means UG is an outer filter. Oops. Okay. So let's prove the lemma. So suppose A is not, right? Suppose, so we have A is not weakly omega below P. Okay, so what does this mean? This means that the set of sigma in P omega 1 of R such that the image of sigma, image of P is subset of sigma, and A intersection sigma to the omega intersection NP is omega in P, omega in NP, right? This set is not, does not contain a cloud, right? Is not in mu. So I want to write mu because I think it's just not important if mu is the cloud filter. So this is not in mu. Okay, but then its complement is in mu, right? Okay, so what is the complement? What is the complement of this set? So this means that the set of sigma in P omega 1 of R such that the image of P is a subset of sigma, and A intersection sigma to the omega and P is not omega in NP is in mu, right? So the complement of this set, mu is an outer filter. So either this set is in mu or is complement. Okay, so what is the complement? The complement is that it's not, because we have the outer filter is fine, right? So measure one many sigmas have this property. This is not the problem that causes, this is not the property that causes problems. The outer filter is fine. That's where we use fineness.
You mean here the property that the image of P is contained in sigma?
Yeah, that's P is finite. Remember, P is a condition in this, right? These are finite functions from integers to reals. So to say that sigma contains this finite sequence of finite set of reals, that there's always measure one many sigmas like that. It means that the other property is the bad property, and so that's what we negate. But now we use Bayer property, right? So this gives me that the set of sigma in the omega 1 over, well, it's not, this one is not if and only if, right? Or is that image Q is a subset of sigma and yeah, I guess it is, right? And there is Q, which is below P, right? Such that A complement intersection sigma omega intersection NP is comega in N Q. This is in U. So we use pair property. If it's not comega, that means the complement will be comega on some open set. Right? So if it's not comega, that means the complement is not meager, which means it will be comega on some open set. Okay, but now you could see where we're going to use normality, right? Oh, this is not what I want. There is a Q in P. I wanted to say Q also comes from sigma because I'm using Baire property. What does Baire property say? You can extend your to another open set, and my Baire space here is sigma to the omega. So Q itself comes from sigma. But that's not what I wanted to write. What I wanted to write is, in fact, this we don't actually need anymore. There is a Q less than or equal to P, such that image of Q is subset of sigma and A complement intersection sigma to the omega, and Q is comega in Q. But my space is sigma to the omega, right? Which is subset to sigma omega. This is mu. So when I fix the Q, then my space is sigma to the omega. So I have to, okay. But now you can see where we're going to use normality, because there are many such Qs for which that's true, and I need to pick one. But how you pick one? Well, you look at a function which sends sigma to the set of all Qs for which this is true, and then by normality you pick one. Okay, so this is the same as there is a Q, right? Such that the set of sigma in the omega 1 bar image of Q is contained in sigma and A complement sigma to the omega, and Q is comega in Q, which is subset of sigma to the omega. Okay, so that is mu. There is a Q like that. But that's exactly what we wanted. So this means there is a Q less than or equal to P, that the complement, A complement, is weakly comega below Q. Right? So assuming our first line fails, we found proof to the second thing is true.
Can you, for clarity, quickly write the function to which you apply normality?
Yes.
Thanks.
Consider f from P omega 1 of R into P omega 1 of R instead f of sigma is let's see. So we could Because you want to fix finitely many sequences, right? I guess that's the problem. Or we could, for one way of doing it. So okay, so if you don't want to apply n times, we could just let's just let me. Defining the function. See below. Okay, so we want to define f. To which we apply normality. You could do it by induction, but you could. Okay, so notice first.
Can't you do just by the range of Q and pigeonhole principle?
Well, it's not the range of Q may not be in sigma, so I want to say. Yeah, I want to say, so you could say for almost all sigma, the set of sigma such that the sigma is closed.
What do you mean range of Q is not in sigma?
But you assume that
It's not, it's just it's a subset.
image of Q is a subset of sigma, right?
Yes. So you see, you want to pick a real. You see what I mean? There's like, there are many things like. Okay, well, so you could say there is an X for every Q in call omega R, such that image of Q is a subset of sigma. There is a in sigma such that A calls image of Q. Okay, this is in measure. This is measure one because I mean, yeah, the set of such sigmas is club. Okay, so then you could now do f of sigma is what? F of sigma is the set of A in sigma such that A calls Q, for which the condition works. A calls Q less than or equal to P, such that A complement in this section sigma to omega and Q is in Q, which is subset of sigma omega, right? And apply normality. And this gives you an A, right? So there is an A in R, such that the set of sigma A is in F, sigma is in mu, then pick and let Q be let's call it by. Okay. All right. So we are, I mean, okay, I'm going slow. I don't know. Maybe I could have gone slower. I don't know whether you prefer me to go slower or faster, but we are kind of almost there, right? What we do next is, this is the ultra filter. So it's, the proof is very similar to the proof I did at the beginning when we had just an ultra filter on lambda. So remember that ultra filter, we converted into an ideal on reals. Here we have very similar situation. We have, this is also an ideal, right? You look at what is your ideal on reals. It's the set of weakly comeager m's below some condition p. That's your ideal, right? So A will have, those are the positive sets. So A will be in your ideal if it's basically not weakly comeager below any condition, right? So you force with that ideal, UG is the ultra filter. Okay, so it's very similar. We started out the same way. Now we're going to show that the two ultra filters agree on ordinals basically when you take the ultra power. That's how we will prove that this ultra power agrees with the mu ultra power on ordinals. That would imply that the ultra power is well founded, and then we will show that this ultra power is actually it gives rise to the dense embedding, dense ideal that we want basically. Right. Okay. So those are the steps. So if there are no questions, we meet next time.
Sorry, why Q is in R to omega? You mean less than omega? Oh,
Yes.
I'm missing some.
Call. I wanted to say in the collapse.
Okay.
Call.
Okay.
Just okay. Ciao, guys.
Ciao.
Thank you.
Bye, thanks.
Thank you.
Yeah.
See you. Bye.